At first glance, the universe seems remarkably uniform. When we observe the cosmic microwave background, CMB, the faint afterglow of the Big Bang, we find that regions separated by vast distances in the sky have nearly identical temperatures, varying by no more than 1 part in 100,000. This smoothness might not seem surprising until you consider a key detail from relativity. Information can only travel at the speed of light. That means that distant regions of the early universe, billions of light years apart, could never have communicated with each other in the time since the Big Bang. So how did they end up so perfectly coordinated in temperature and structure? This deep puzzle is known as the horizon problem. Let's explore the nature of the problem. According to the standard Big Bang model, before inflationary theory was introduced, the universe has a finite age and a finite speed limit, light speed. As a result, there is a maximum distance over which any influence, like heat, pressure, or light, can travel. This distance defines the cosmological horizon, the boundary of causal contact. Two regions on opposite sides of the sky, say 13 billion light-years apart, could not have exchanged signals, energy, or even shared a common history within the first few 100,000 years of the universe's existence. And yet, the CMB shows that these regions have nearly the same temperature, a striking uniformity that should be impossible if they evolved independently. It's a bit like walking into a room and finding 2 cups of coffee on opposite tables that are exactly the same temperature, down to a tiny fraction of a degree, even though they were never poured from the same pot or allowed to mix. Something must have happened to synchronize them early on, some process that allowed distant parts of the universe to equilibrate before the cosmic microwave background was released. So how do we resolve this apparent contradiction? The leading explanation is a theory called cosmic inflation, first proposed in the 1980s by Alan Guth and later refined by others. Inflation suggests that a tiny fraction of a second after the Big Bang, during this ultra-fast expansion, regions that were once in causal contact and could share information, equilibrate temperature, and smooth out differences, were blown up to cosmic scales, far beyond each other's current horizons. In other words, what we now see as separate and unconnected regions of the universe were once right next to each other, part of a tiny, uniform patch that had time to reach thermal equilibrium. Inflation stretched this tiny, smooth patch to become the observable universe. This elegant mechanism solves the horizon problem by redefining what was once connected. Even though parts of the sky are out of contact now, they were causally linked before inflation and thus could evolve in harmony. But inflation does more than just explain uniform temperature. It also predicts the tiny quantum fluctuations that, when stretched to cosmic scales, seeded the large-scale structure of the universe, galaxies, clusters, and voids. These predictions match the observed pattern of fluctuations in the CMB almost perfectly, lending strong support to the inflationary picture. Still, inflation is not without its own mysteries. What triggered inflation? What field or particle drove it? How did it stop? And are there alternative explanations? Some theorists have explored bouncing cosmologies, varying speed of light models, and emergent space-time theories, though none have gained the same empirical traction as inflation. So how did distant regions of the universe reach the same temperature without ever talking to each other? Under the standard Big Bang model alone, they couldn't. But inflation provides a compelling solution. They talked early, then got pulled apart so fast that they can't talk anymore. It turns the paradox into a window into the deepest dynamics of the early cosmos. Could resolving the horizon problem help us unlock even more fundamental insights about quantum gravity, the birth of time, or the multiverse itself? Many physicists think so. In trying to explain the sky's uniform glow, we may have stumbled on the seeds of a grander theory of cosmic origins. The horizon problem arises from the observation that distant regions of the cosmic microwave background, CMB, exhibit nearly identical temperatures, despite being separated by distances too vast for them to have ever been in causal contact. In a universe expanding at a finite speed, light from one region should not have had enough time to reach another and equalize their condition. This discrepancy between observed uniformity and expected thermal differences challenges our understanding of early universe dynamics. It forces us to ask how disparate regions could achieve such remarkable homogeneity without having interacted. Example, measurements of the CMB revealed temperature fluctuations of only 1 part in 100,000 across the sky, even though many regions could not have exchanged energy due to the speed of light limitation. Analogy, it's like discovering that isolated villages on opposite sides of a vast desert all celebrate the exact same festival with identical customs, even though they have never communicated with each other. The paradox is defined by the conflict between the expected causal disconnect in the early universe and the observed uniform temperature across the CMB. In standard Big Bang cosmology, regions separated by more than the particle horizon should have evolved independently and developed different temperatures. Yet these regions appear nearly identical in temperature and other physical properties. This mismatch between theory and observation lies at the core of the horizon problem, prompting re-examination of early universe physics. Example, when cosmologists calculate the distance light could travel from the Big Bang until recombination, they find that regions more than a few degrees apart in the sky were causally disconnected, yet the CMB temperature is uniform across these vast angles. Analogy, it's like two strangers on opposite sides of the world inexplicably sharing the same exact accent and dialect without any possibility of having influenced each other. The causal structure of the early universe is determined by the finite speed of light, which defines the particle horizon, the maximum distance over which particles could have interacted. In the standard model, the universe was too young for light to travel between distant regions, preventing them from reaching thermal equilibrium. As a result, we would expect noticeable temperature differences in the surprising uniformity suggests that some mechanism must have allowed these regions to share information earlier in the universe's history. Example, calculations show that regions more than about 2 degrees apart on the CMB sky could not have exchanged signals before recombination, yet they show nearly identical temperatures. Analogy, it's like expecting two separate classrooms isolated from each other to have completely different test scores, only to find that both classes achieved almost identical results. Inflation theory proposes a period of extremely rapid exponential expansion in the early universe that stretched a small causally connected region to encompass the entire observable universe. Before inflation, the entire region now visible in the CMB was in thermal equilibrium, allowing for the observed uniformity. During the inflationary phase, these regions were rapidly expanded beyond each other's horizons while preserving their uniform conditions. This mechanism elegantly resolves the horizon problem by ensuring that all observable regions were once in causal contact. Example, according to inflationary models, a tiny uniform patch of the early universe expanded to become the vast, homogeneous cosmos we see today, explaining the uniform CMB temperature. Analogy, it's like inflating a perfectly smooth balloon from a very small size to a huge one. The originally smooth surface remains uniform even as the balloon grows immensely large. Beyond inflation, alternative models such as bouncing or cyclic cosmologies have been proposed to explain the CMB's uniformity. These theories suggest that the universe may have undergone previous phases of contraction and expansion, allowing distant regions to equilibrate before the current expansion phase began. Although these models provide intriguing possibilities, they must also confront the observational evidence that supports inflation. Each alternative approach seeks to reconcile the apparent causal disconnect with the homogeneity observed in the universe. Example, some cyclic models propose that a prior contracting phase allowed the universe to homogeneous before bouncing back into expansion, thereby solving the horizon problem without invoking inflation. Analogy, it's like stirring a pot of soup repeatedly so that every spoonful tastes the same, even though the soup was once separated into different layers. The resolution of the horizon problem has profound implications for interpreting the CMB and the formation of large-scale structures. A uniform CMB supports the idea that early universe processes such as inflation played a crucial role in homogenizing conditions before the universe expanded to its current size. This uniformity also provides a baseline from which the small anisotropies which seeded galaxy formation can be understood. Hence, the horizon problem is not only a puzzle about early universe causality, but also a key to understanding cosmic structure formation. Example, observations by satellites like WMAP and Planck have confirmed the remarkable uniformity of the CMB, supporting the predictions made by inflationary cosmology. Analogy, it's like finding a nearly flawless canvas that only reveals subtle brushstrokes upon closer inspection, indicating that an artist carefully prepared the background before adding detailed highlights. High-precision measurements of the CMB and large-scale structure in the universe provide strong evidence for inflation as a solution to the horizon problem. The minute anisotropies in the CMB are consistent with quantum fluctuations stretched to cosmic scales by inflation, these observations are backed by theoretical models that describe how rapid expansion can generate a uniform temperature across the sky. Continued refinement of both observational data and theoretical frameworks further supports our current understanding of early universe physics. Example, the nearly uniform CMB, punctuated by tiny temperature fluctuations, matches predictions from inflationary models and has been confirmed by multiple space missions. Analogy, it's like verifying a recipe by tasting a dish that is almost uniform in flavor, with only slight variations that hint at the secret ingredients used during cooking. Despite the success of inflation in addressing the horizon problem, significant theoretical challenges remain, including understanding the nature of the inflaton field and its potential. Critics argue about the initial conditions required for inflation to begin and how it naturally ends. Furthermore, reconciling inflation with quantum gravity remains an open question in theoretical physics. These unresolved issues continue to fuel research and debate in cosmology as scientists work toward a more complete picture of the early universe. Example, some models of inflation require fine-tuning of parameters, and alternative scenarios are still under active investigation to address these limitations. Analogy, it's like having a sophisticated machine that works perfectly in theory but whose inner workings remain somewhat mysterious and require further fine-tuning before they can be fully trusted. Future research aims to further elucidate the mechanisms behind the horizon problem through improved observational tools such as next-generation CMB experiments and gravitational wave detectors, as well as advanced theoretical models in quantum gravity. These efforts may provide new insights into the pre-inflationary universe and offer alternative solutions that complement or refine inflationary theory. Understanding the horizon problem is key to unlocking deeper truths about the origin, evolution, and large-scale structure of the universe. Ultimately, resolving this paradox will have far-reaching implications for both fundamental physics and our cosmological worldview. Example, upcoming missions are designed to measure CMV polarization and gravitational waves with unprecedented precision, potentially revealing new details about the inflationary era and the early universe's causal structure. Analogy, it's like upgrading from a standard telescope to a cutting-edge observatory that not only captures distant galaxies but also deciphers the hidden patterns of light that reveal the universe's earliest secrets.